And we're live.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we've got a really interesting hangout planned for you today. We're going to be talking about white dwarfs, cataclysmic variables, the Hubble Space Telescope, amateur astronomers, all kinds of really interesting topics today. So the basic premise of today is the astronomers using the Hubble Space Telescope wanted to try and answer the question, can white dwarf stars grow in mass, among other things. That's one of the questions they were trying to answer. And today we're going to explore that. With me today, as always, is my good friend and colleague, Dr. Carol Christian. She's from the Space Telescope Science Institute also. She knows about all things Hubble, and she's going to be helping me with this discussion. Also is Scott Lewis from knowthecosmos.com. And he'll be on hand to help provide his unique perspective as well. Before I get to the introductions of our group today, though, I want to point out that we hope you'll interact with us. We hope you'll send questions. Already, I'm encouraged by what I see in the Q&A app. There's already a lot of things there for us to get to, and we're going to, I promise, we'll get to as many as we can throughout the course of the discussion. But if you're wondering how you can interact, one of them is the Q&A app. You'll see that if you're watching this on YouTube or on the Google Plus event page. Just type in a question or a comment, and we'll see it come up on our window pane. Also, the YouTube comments. Feel free to leave a comment there. You can tweet using the Hubble Hangout hashtag. One day I'll get that without stumbling.
You got it.
I'm monitoring that on as well as the Google Plus event page. So there's lots of ways for you to leave us comments. Scott, Carol, and I are looking at all of those, so we encourage you to ask us questions. Okay, so today we have with us from the University of Warwick, we have Dr. Boris Gensecki. He was the PI of the program, and he will be giving us a background of some of the scientific motivations and what they were doing, what they were trying to accomplish scientifically with the Hubble Space Telescope. Also, Dr. Nolan Walburn, also of the Space Telescope Science Institute. He's a member of the COST team and the Cosmic Origin Spectrograph team, who was also responsible for various things on the project. Alan Welty is here. No, he's not here. I'm sorry, Alan. He did. And we have Gordon Meyer and Ardo Oksanen who were two, and here's the way Boris describes them. He describes them as two of the most professional amateurs you can imagine. They operated remote telescopes, and without them, we would certainly have struggled to complete this HST program. So welcome, guys. We also have Arnie Hendon from the American Association for Variable Star Observers. He was responsible for organizing some of the campaigns. So welcome, Arnie. And we also, and I think that covers everybody. So let's go ahead and get started. And Boris, I'd like to start with you as the PI. Give us some background of what you were trying to accomplish with this. You had been given 122 Hubble orbits to accomplish what you wanted to accomplish. So give us a background. What were you trying to do?
Okay, Tony. So I guess you've talked about Type 1a supernova in past hangouts, which are among the most powerful explosions in the universe, and they have been used to discover dark energy and led to the Nobel Prize in Physics in 2011. And one big problem is that we still don't know exactly what kind of stars explode under what conditions to make a Type 1a supernova. Now, most astronomers agree that it's probably white dwarfs that reach the so-called Chandra-Sekar limit, a maximum limit that they have, and then they explode. And that means these white dwarfs need in some way to grow in mass. And so that was the key question we want to address in one type of white dwarfs in binary stars.
Okay, Boris, let me just interrupt you very briefly for a moment here and say one important thing about Type 1a supernovae that I want to make sure we mention, and that is they are basically cosmic yardsticks. They are very important for measuring how far away things are in the universe, because when they do explode, they explode with a known intrinsic brightness, and that is a brightness that they would be if they were right next to us. And if we see how bright they are very far away, and we know how the light falls off with distance, we can figure out how far they are. So that's why Type 1a supernovae are so important. And as Boris said, we don't know exactly the kinds of stars that cause them, which I guess surprises me, Boris. I thought we did have a good handle on that.
Well, it depends on the fashion that you follow a bit. At the moment, probably most people would say that they believe it's merging double white dwarfs, two white dwarfs that merge together and then exceed the Chandrasekhar limit. But there's still quite a number of problems with that model as well. So we wanted to explore an alternative route that may lead to type 1a supernovae. And so the system that we were interested in are called cataclysmic variables. And in those systems, you have a white dwarf that is accreting material from a relatively low mass companion star, so something like the Sun or even less massive than the Sun. And
I think Scott might have a diagram on that real quick to put up.
Okay.
Here we go. Go ahead. So yeah, this is just showing what Boris is talking about.
Okay, so in a cataclysmic variable, you have a white dwarf that accretes material from that companion star, and you form an accretion disk of mainly hydrogen that then flows onto the white dwarf. And probably 20, 30 years ago, astronomers have excluded this kind of systems as potential type 1a progenitors because they go periodically through a process which is called the classical nova, where the hydrogen that flows on the surface of the white dwarf starts to burn and then ejects all the material that has been accreted back into space. So if that really is true, these white dwarfs, they couldn't grow in mass. Yet there are some question marks to those problems, and some recent studies suggest that, well, the white dwarfs in cataclysmic variables are actually more massive than we expected them to be. And so that's why we initiated this large HST program to measure accurately the masses of 40 cataclysmic variables to have a bigger statistical sample on a bigger group of stars for which we have accurate masses and can learn something about the mass distribution of these white dwarfs.
So this is Carol, can I just ask a quick question here? So if there's a distribution of masses of these objects called cataclysmic variables, is it possible that some could be supernova and some could be nova, or you don't know yet?
We don't know yet. Probably if any of them become supernovae, it's a very small fraction of that type of stars. Probably only the heaviest one will ever get to that point.
Okay, so you were looking. So you wanted to see if these white dwarfs were getting more massive, and it looking at that diagram that Scott has there, I can already see that there are some challenges to actually measuring the white dwarf itself. You want to explain some of the real problems with making this observation?
Yeah, sure. So one problem is that in these cataclysmic variables, if you observe them at optical wavelength, so from the ground with a conventional telescope, what you see is mainly the accretion disk and the companion star. And they're much brighter than the white dwarf at optical wavelength, and so you can't actually learn much about the white dwarf, let alone its mass. And that means if you want to study the white dwarf, you need to move into the ultraviolet and obtain observations at wavelengths that are like much shorter than the light that can penetrate through the Earth's atmosphere, and that's where Hubble comes into play, because Hubble is currently the only instrument that can do ultraviolet observations.
So let's bring Nolan in on this. So Nolan, is this where you took it over? Is this where you were involved with the observations themselves? That's the world coming.
Is that very ominous?
Yeah, did I do that? Sorry.
That's great.
And
now Nolan
right there.
Yes, we have.
Yeah. Some introduction. So, well, yes, partially. I should, I guess, say deference to a colleague who's since left and gone back to Italy, Elena Masson. She really was the staff contact for this program initially, and did, I would say, most of the work, but she's gone on to a different position now, and so I picked it up after she left. So we heard about ultraviolet and the Hubble, and so Hubble is the only observatory we have that can do this kind of work that Boris wants to do. And so we have some spectrographs, one of which you use, the cosmic origin spectrograph, and they can observe in the ultraviolet, so they have ultraviolet sensitive detectors. Unfortunately, these detectors are very susceptible to damage and even destruction by over-illumination. And so for every observation we do with any of these detectors, we have to do a very careful screening of the target and even the field around the target to make sure that it's safe, that the count rates won't be too high for the safety of the detectors. And that's a big job. It's, as you can imagine, we have thousands of targets a year, and somebody has to do that for each one. That's a good part of my time here, of what I do on my technical side. So
you're always worried about whether or not. I mean, people forget this. Hubble is designed to view very, very faint things, and so even something reasonably bright can do some damage to Hubble. So do you spend a lot of your time worrying about things like that? Is that one of your jobs?
Yes, exactly. We have to screen every target, and we have software systems to help us do that. There is a detector for each a limit for each configuration involving a given detector, which aperture is being used, filters, whatever, and we can calculate what the count rate will be given the input data about the target, and so we check that for everyone to make sure that it's safe. So that was done for all of Boris's targets, and I have to say, maybe semi-humorously, that there was kind of an oh-no factor when his program arrived, because he had 40 some of these targets, and it's a lot of work. And not only do they have to be screened in their quiescent state, which we hope and intend to observe them in, but these objects are also subject to unpredictable, almost instantaneous flares that increase the ultraviolet brightness by a huge factor, so it could be perfectly safe in its quiescent state, which we have data about, and destroy the detector if it happened to have an outburst during the observation. So
Boris told me that could be on order of anywhere from 3 to 7 magnitudes, right? I mean, that brightness.
Yes.
So this is a real threat.
It is. It's a huge amount, and there are onboard safety mechanisms which are designed to shut the detector down in time if it detects such an overillumination, but such a sudden huge increase might get through and damage something. Also, if we have such a shutdown, it fouls up the whole Hubble schedule, and things have to be redone, and time may be lost, so we want to avoid that. Well, we can't predict this, and so we can't be absolutely certain that it's not going to happen, but we've thought about the statistics and how frequent these outbursts might be, maybe centuries in this. Well, it's different. There are different subcategories of these, which Boris can tell you about. I'm not an expert on it, and but their properties are known, and we can predict statistically how often these outbursts might occur, but not when one is going to occur in a given object. So the mechanism we settled on is to make sure that the object is still in its quiescent state and safe according to our screening 24 hours ahead of the observation. And of course that requires a lot of work on the part of a lot of people, and including
So let's get to that first. So part of the problem is you needed observations, because before you point the Hubble anywhere, you want to make sure that everything is still safe, and so you need somebody to monitor these targets. So all these targets that Boris came up with needed to be looked at right before you turn HST over, and there was a system you guys put in place for that, right? And who would Arnie? Would you be the one that coordinated those efforts, or would that be Boris? I want someone to talk about who was doing the monitoring of these targets before HST was pointed.
Well, it was sort of a combination. Boris certainly was the one who talked to HST to let them know the results of the monitoring that took place. But I was the one who helped coordinate the various amateur activities related to that. We generated finding charts for each one of the objects, and then set up a campaign for each of the objects as they were coming up on the HST queue to have the amateurs observe these objects and monitor them, and to ensure that they hadn't gone into outburst. As it was mentioned, the outburst is many magnitudes in size, so it's really easy to see whether an object is in quiescence or whether it's far brighter than that. So it's a very simple observation to make, but it's one where you need to have people geographically distributed across the globe, so if they can catch the any kind of an outburst just as it starts beginning, especially within that 24-hour window that HST required. So we enlisted the aid of a large group of amateurs, partly from the AAVSO itself, but then also the various members, various observers around the globe who also submit observations to us. And everybody got very enthused about the project, even though there's 40-some objects. I mean, it's a lot of observing that has to be done. But the amateurs were up for it, and they had observations for every single one of those targets within the time frame that HST required.
So we have Gordon Myers and Arno Oksanen here as examples of, I guess you were two very instrumental amateurs in getting these observations done. Are you guys members of AVSO?
Yes, I am.
Okay. Yeah. And so, do you have really? Do you guys have a backyard full of really amazing equipment, or do you have just regular off-the-shelf telescopes? I mean, tell us what you use, and I'll start with Gordon and then go to you, Arto. Arno.
Yeah, actually, I was using some scopes that were remotely located. A fairly large scope down in Australia, and then also had access to a scope in New Mexico and also in Spain. So we were often trying to
now, how did you get access to all that? How did that happen? You don't own telescopes in all those areas, do you?
No, there's some organizations that allow you to rent time on telescopes by the minute, and you can coordinate with them and get things scheduled so that you can, observe targets at various times, and that worked quite well, other than when the clouds would show up, or if somebody else already had the scope scheduled. But I think it was very enjoyable for the amateurs because we got a chance to really, help the scientific observations go off on schedule, and I think that's one of the things the amateurs enjoy the most.
Now, is this like itelescope.net? Is that similar to what's going on there?
That's the one I use. Yes.
Okay. Yeah.
It works very well.
I've worked with them in the past, and they're fantastic.
Yeah, I want to have a hangout on just that, what it's like to use some of these various online telescopes at some point in the future, because I think that's a resource that's becoming more and more valuable, and it might even be better, and maybe we won't talk about it here, but it may even be better than buying your own scope or something, maybe, who knows, I don't know, but it is an interesting idea. Is that what you did, Arto, as well? Did you do that, or what did you do?
Yeah, I was using remotely operated telescopes as well.
Also, you were also using online telescopes?
Yes, one in Finland and one in Chile.
So let me get this straight. Are you guys paying for this out of your own pocket? You guys are buying this telescope? Is it expensive?
And the telescope I'm using in Finland, it is owned by my astronomical club. It's a club telescope. And the one in Chile, it's owned by a friend. It's a private telescope, but I can use quite freely of it.
Man, amateur astronomy has sure changed since I was doing it. I know that. It's like the internet has made everything possible. Who needs, no such thing as a cloudy night anymore. Just go to another part in the world.
So can I ask Arto a question then? So you have a club then, and you own one telescope or several telescopes, and then you have to make the case. You have to kind of propose to your group, hey, I want to do this project. Oh, that's a great question.
Yeah.
Yeah. We don't have too many observers, but we have basically 1 hour per observer per night that we are sharing. So first come, basically.
Nice. Okay. So Boris, how hard was it to coordinate all of this? I mean, you're getting ready to point the Hubble somewhere. You don't know if it's scary or not. You don't know if you're going to burn out detectors, and you and Nolan are, making sure. What was that like? Give us a sense of what that was like to get all that put together.
It was frightening because these systems, they're unpredictable. As Nolan said, statistically we can tell how often the outbursts are every 3 months, every 6 months, but you never know, they could be tomorrow. And so every single time that I got an email that the next HST observation is scheduled, I would get in touch with Arnie and send out an email to the amateurs I know personally and start to collect observations. And then we had 3 or 4 near misses where the systems went into an outburst about a week before the HST observations. And then the question was, would they fade rapidly enough that it's safe for HST to observe? And so the kind of closest call we had was one system very far in the southern hemisphere. The problem there is that the southern hemisphere doesn't have a lot of land, so there are not many telescopes that are available. It's Australia, South America, and South Africa.
Right.
And so I was myself just on a trip to Chile and got an email while I was in the taxi going to the observatory there that one of the stars scheduled for HST observations later that week had gone into outburst. And so I was frenetically emailing Arturo and some other people in South Africa that they get onto the star. And so they did what they could do, and they could demonstrate to Space Telescope, demonstrate to Nolan and Elena that the star was fading rapidly and that it was back in quiescence about 12 hours before HST would salute to it. And so then they were happy and they said, okay, go ahead, we do the observation.
Wow, that's amazing.
I know. So for the benefit
so it was really real time, 24 hours working on that program to make sure that the communication works, that we can fill in gaps if there's bad weather in one continent, that we can work from somewhere else. And people like Arturo and Gordon just responded so brilliantly to my requests over and over again.
That's awesome. So for the benefit of those who might be watching that might want to do this kind of thing, get involved in this kind of thing with Hubble science, how did you guys find out about it, Arto and Gordon? What was it through ABSO?
Yeah, in my case, it definitely was. Yeah, I mean, the alerts from AAVSO were the ones that I really tied into, and then through those, ended up doing emails directly with Boris in several situations. But yeah, it was the coordination through AAVSO that really made it all happen. Okay, and same for you, Arto. Or you found it out the same way?
Yeah, I think so. I learned it by AAVSO, but probably got the email from Boris as well.
Well, there you go, Arnie. There's a good plug for why you need to get more members or get a member of the organization. What's it like? Tell us how to do that. What is ABSO, and how can people sign up?
Well, AVSO.
I always say ABSO. It's just an old habit. Sorry.
Yeah. Well, I mean, there's ABSO, AVSO. You know, you pick your way of pronouncing the acronym. That's fine with me. But it's the American Association of Variable Star Observers, and what that means is exactly what it says. It's people who have an interest in variable stars. They can be professional, they can be amateur, they can be just interested in doing database design, whatever. But we give equal weight to everyone. We do have a website that you can go to, aavso.org, and on there's a way in which you can join the organization. It's not that expensive. We do actually have a robotic telescope network that you can get to for free if you're a member. And so it's, I think it's an exciting time for astronomy in general and for the amateur community in particular.
And for the professional amateur collaboration world as well. I mean, there's a lot of these kind of collaborations happening now as a result of your efforts. I remember in the 70s when I was a member of AAVSO, what I did was I took my little C8 out and I would just plot light curves of different variable stars, send them in via mail, and you guys would process them and make it available to professional scientists for people who needed light curves of variable stars. That's what I did when I was in high school. And
well, I have a question actually about the process. So you're sending out alerts, and the members are responding. Do they go directly to Boris then and start reporting? They make measurements and report the measurements? Does somebody collect all the observations for use later? I mean, maybe those observations are worth something in reference to the HST observation. So what about the data and all of that? What happens with all of that?
Well, Carol, all that happens. We do have an online publicly accessible database, and we encourage all the observers to submit their observations to that database. And it's real time, so that means then that Boris or whomever can actually access the database and see what the latest reported observations are. In addition to that, we have online forums, and so there was a forum that was set up, and people would report any kind of immediate notification there. It may not have been a quality observation yet, but they wanted to alert somebody about it. And then finally, Boris was available. It seemed like 24/7, and so you could just email him and let him know if you saw anything that was important. So we encourage that as well.
Okay, well that is a great resource. So I would encourage anybody interested in getting involved to go to that website and see and learn more about it themselves and get involved. I mean, this is the best. This is a golden age of astronomy for amateurs as well, and you can really help professional astronomers in ways that have never really been before possible. So I would encourage you to do that. I want to go back to the science a little bit now, and then I want to get to some questions and comments that we have on the various things. But so we have these white dwarfs. Nolan's waving. Yes.
Yeah, I think it's important to add a bit more about what we actually have to do here to make this work at the Hubble.
Okay.
We kind of left it that, yeah, we have to know whether a field is safe before we point the Hubble there, but it's not quite that simple. As you know, the Hubble is in low Earth orbit, goes around the Earth every 96 minutes, and we can't have continuous communication with it. And the way it works is that a mission schedule is prepared and sent up to the telescope once a week. I believe it starts on Saturdays or Sunday, I forget, and then runs for a week. So, but as I said, we're making this decision 24 hours before the observation. So clearly there's an incompatibility there. So a very a rather complex and intricate system has been developed to do this, involving a lot of people. Actually, not only at one level, we heard how the observers provide the information. Boris coordinates it, sends it to me or to Elena, and then I give an approval if it's safe 24 hours in advance. But in order to make that happen, the telescope has to be scheduled in a very special way. And the way this is done is that it's set up so that the telescope will go and point at a blank field very near the target, and there is communication possible with the Hubble some hours a day through the NASA tracking and data relay satellite system. So all of this has to be set up and coordinated with our engineers. At some point it's out of the hands of the astronomers and in the hands of the engineers because we don't talk to the telescope. And engineers here at the Institute and then at Goddard Space Flight Center where the vehicle is controlled. So there's a flag set on board, and Alan Welty isn't here. He's one of the engineers who does this and knows a lot more about the details than I do. But in broad terms, this flag has to be cleared so that the telescope will go to the real field and not to the blank one after the OK comes in at 24 hours in advance. And hopefully that's not 3 a.m. or 2 a.m. or whatever. Because of our budget cuts, NASA only operates 9 to 5 or 8 to 5 now down there. So it's a bit intricate. But we have managed to do it, and this flag gets cleared, and then the telescope actually goes and points to the real target and does the observation. And Boris, I don't recall where any, I think there were among your 40-some targets, 1 or 2 that were actually aborted, and the observation was not conducted. Is that true?
That's right. Out of 41 targets, we lost 1. And that one, that was just one of those cataclysmic variables that just behaves in a completely unpredictable way. It didn't go into a proper outburst, but it was brightening and fading in a very irregular fashion. And I remember I was having dinner, and Elena called me while it was dinner time over here in the UK, and we were discussing it. And she said, "I'm sorry, it's just too risky to go ahead." And she said she cannot sign that one off. So we lost that 1 star, but all the other 40 were successfully observed. Yeah. So that's a really great success.
So yeah, it is. It's a tribute to everybody involved all over the world that we achieved that success rate. And but it shows there's a human judgment involved here too. It's in some ways kind of like a legal criterion beyond a reasonable doubt. And it's not only for these observations; it's for all Hubble observations. We can never prove 100% that something is safe, but it's up to contact scientists in the ultimate instance to decide whether he or she feels comfortable that to the best of our ability and the best of our knowledge this target is safe. And that's what applied also to this rather unusual case.
Nice. Okay. Good summary. So that was good to know. So like I said, I want to get back to the science a little bit. You were trying to answer the question. We said this at the top of the show. about you were trying to find out if these white dwarfs in these binary systems actually grew in mass, and if they did, how efficient is that process of getting larger? So here we have a white dwarf. They are all of the roughly the same size, correct, Carol? All white dwarfs are more or less the same mass, right? You're muted.
Actually, Boris should answer that
okay.
question.
Okay, I was trying to get.
No, he actually told us that they're different masses.
Okay. But the reason.
The progenitors also are different sizes, but then above some mass size, they can't become white dwarfs anymore because they have too much mass. So there is a limit, and then beyond that, they become something more exotic, although white dwarfs are pretty darn exotic anyway.
So I guess I'm confused about, well, first of all, let's just get to the punchline. What'd you find out? Are they getting bigger, Boris? Can you hear me?
Tony, I missed that.
Oh, I was asking. So, what'd you find out? Are they growing in mass?
Well, we have just we have obtained the last observation of this problem just in March, so we are still in the process of analyzing the data. And it's not as straightforward just that we measure the mass straight away from the observation, because another piece of information that we need to know is the distance to these stars, which together with the Hubble observation, we will then be able to convert into mass. But just coming back briefly to the point about white dwarf masses, your textbook white dwarf on the sky has a mass of about 0.6 solar masses, so 60% the mass of the sun.
That's what I was remembering.
And so most white dwarfs have that mass. So the average mass is 0.6. And looking at cataclysmic variables, the data we had before this HST project on something like 20-25 stars showed that they have average masses of 0.8 solar masses, so 80% of the mass of the sun. So they're about a third heavier than your average single white dwarf. And that was the clue why we think they may grow in mass. Now, the few objects we have analyzed in a little bit more detail from the HST project, they all confirm the same suspicion that they are more massive. So they come in at masses of 0.8, 0.9 solar masses.
So a white dwarf just hanging out in the galaxy is about 0.6, but one in a system like this is a little bit heavier. And you think it might be due to this accreting material, or that the process isn't very the process isn't very efficient. Somehow masses is not all of the masses being released, right, in the explosion.
Yeah, well, so the kind of fact that we are working towards at the moment is that these white dwarfs and cataclysmic variables are definitely much more massive than your typical single white dwarf in the galaxy. And there are basically just two explanations. Either they grow in mass, or they are just born with a much higher mass right at the beginning. And making all these systems with much more massive white dwarfs is incredibly difficult to explain. So mass growth seems to be the natural explanation, even though there are quite a number of people who feel uncomfortable about that as well. But that's the good thing about science. We have two options, and both of them don't work.
So,
could I ask?
Go ahead.
Sorry, just another question. So at the beginning of this course, you were talking about looking for causes for type 1 supernova, and you mentioned the binary systems. So where in the spectrum of cataclysmic variables and nova are the binary systems? Because they can be white dwarfs as well. Is that correct?
I missed half of your question. Repeat that, please.
The progenitors for type 1 supernova, you mentioned binary system, white dwarfs.
Yeah.
So where do they fit in this scheme?
They fit in this scheme in the sense that you need to have a different type of stellar system to make two white dwarfs in the first place. And so you need to have two fairly massive stars that can evolve relatively rapidly into white dwarfs, both of them, and then merge within the age of the galaxy to become a type 1a supernova. So they're a different breed of binary stars. In general, type 1As, I think nobody has any doubt that type 1As must be related to white dwarfs in some kind of binary stars. The big question is, what kind of binary stars are those? And my personal feeling is there are probably more than one type that can work. So
Scott has a little diagram, a little cartoon of a couple of white dwarfs orbiting to sort of underscore what you're talking about there. I guess one thing that worries me, though, is that you said that you still needed to know their distances to really know if they were gaining mass. I thought Type 1a supernovae were yardsticks. They told us how far away things were. Don't you know that?
That's right. If you want to measure distances
I'll let you comment,
to
Nolan,
galaxies
just a
far
second.
away, if you want to measure distances to galaxies far away, then you want an exploding white dwarf in it. But here we are looking at the actual white dwarfs before they explode, and so for the measurement we have in mind, we need to know the distance. And just to make it clear, these white dwarfs, they're really nearby. We are talking about a few 10 and at most a few 100 light years. So they're basically in our
so you can use parallax to figure it out.
Exactly, and so we can use parallaxes, and the European Space Agency has launched their mission Gaia just last, I think it was January, that will provide us with super accurate distances within the next few years. So we can get some preliminary answer within the next year or so, and then the final answer will have to wait for about 3-4 years before we have the final distance measurements.
All right, great. Thank you for clarifying that. I will get back to what parallax is in a minute, but let Nolan make his comment. Go ahead, Nolan.
Yeah, thank you. I have an uncomfortable feeling that if there are people listening who aren't familiar with the basic astronomy here or haven't heard the previous hangout on supernovae or whatever, they may be a bit confused. And so I think it would be useful just to run through a few basic things. A white dwarf, for a star to be a white dwarf, to have this phenomenon of electron degeneracy in its interior that holds it up and prevents further collapsing, there's a mass limit that Subrahmanyan Chandrasekhar first derived and won the Nobel Prize for. And it's about 1.4 times the mass of the sun. So we think that stars up to maybe as massive as 8 solar masses can lose enough mass to get down to that limit and form a white dwarf. Has to be 1.4 solar masses or less. So if you just have a single star forming a white dwarf, that's it. It won't do anything else. But in a binary system, if it's either 2 white dwarfs that can merge and therefore exceed that limit of 1.4, you're going to get a 1A supernova. Or in a normal, in a binary with a white dwarf and a normal star that Boris is favoring, the normal star can lose mass and transfer it to the white dwarf. And I thought there was a bit of a confusion there. These outbursts that we're concerned about, these are not explosions, nuclear explosions. They are gravitational accretion events, which produce an instability and produce this outburst of ultraviolet light. What happens, though, in these binary systems is a phenomenon that we call novae. And so material is transferred from the normal companion to the white dwarf, gets very hot, and at some point there is a nuclear explosion on the surface of the star, and that produces a nova, and it ejects mass. So if that happens before the Chandrasekhar limit is reached, how can you ever get a supernova? Because you transfer some mass and there's a nova and it loses a bunch and then come back and over and over again. And some of these novae are known to be recurrent. That's typical. How do you transfer mass onto the white dwarf from what kind of a star and not have it get lost in nova so that it can build up to exceed the Chandrasekhar limit and produce a supernova? So that's the basic phenomenology that we're talking about here, and I just thought it might be useful to review that.
Oh, that was great. I'm glad you did that. That was something I tried to do periodically throughout the discussion, but that was a really good overview. So thanks for that. I appreciate it. And you're absolutely right. We need to be. I hope that clarifies some of the astronomy that we're dealing with here. So we're still working on the results. You're still analyzing the data that everybody took, and presumably all of the data are in good shape, and the Hubble wasn't blinded by any of this, thanks to the amateurs. So let me go to some of the questions here that I'm seeing on the Q&A app. Let's see. I want to go. How can a telescope measure? And this is from Pardue Madipali, I believe. Forgive me if I mispronounce it. This is from the Q&A app. How can a telescope measure the distance of a far celestial body from us. A telescope receives light from the body, and the image of the body is magnified. Then how can it measure the distance? So how do we know the distances to things? I mean, how can a telescope tell us this? And I'll give that to, let's go with you, Boris. Can you give us a little, take that on?
Yeah, I can give it a try. So besides collecting more light than you can collect with your eye or your binocular, a telescope can measure very, very accurately the position of a star in the sky. And so you have to imagine that as the Earth goes around the Sun, the apparent position of a nearby star changes because of our motion. So basically, if you look at the sky, that star that you are looking at would, over the course of a year, describe a little circle or a little elliptical, a little ellipse on the sky. So it looks like the star is moving, but that's just the reflection of the Earth moving, your telescope moving. And so that's what we call the parallax motion of stars. And from that, through basic trigonometry, you can calculate the distance if you measure the size of that parallax motion. Now, to do that, you need to measure the position very, very accurately. And if you try to do that from the ground, you are a little bit in trouble because the Earth's atmosphere is turbulent and blurs the images of the stars. And so you are limited to how accurate you can measure the position. And that means from the ground, you can measure parallaxes to a few hundred light years at most. And if you want to measure distances of stars that are further away in our Milky Way, then you need to have telescopes in space that are above the atmosphere and can measure the position much, much more accurately than you can do from the ground.
Very awesome. I'm glad we worked that in. Perfect. So there you go. That's what parallax is. And here's from Hamza Arshad. Also from the Q&A app. I can't select these questions, unfortunately. Otherwise, I'd bring them, make them prominent. I am a student in Birmingham. I think it says NEET Boris actually, but I think it said it met Boris actually. I was wondering, what is the Chandrasekhar limit? Now, Nolan touched on this very briefly about this idea of electron degeneracy. Anybody want to give a real brief answer on what that might be? And how about you, Nolan? You gave a pretty good summary before. Tell us about what is the Chandrasekhar limit. I mean, what is electron degeneracy?
Sure. At a very high level, I'm sure Boris could give a far more physical explanation, but at a high level, you have to go back really to what a star is, and star formation. A star is a huge mass of gas in balance between gravity inward and the pressure from the nuclear reactions in its interior outward. And but at some point, the fuel that it's burning is going to get used up, and the gravity will never go away. It's always there. But when the nuclear reactions and the pressure stop because the fuel's used up, then there's a problem. And so there are various outcomes of this problem depending on what the initial mass of the star was. And we're talking here about relatively low mass stars with initial masses less than about 8 solar masses, and they have a solution which is fairly quiescent. They can lose enough mass from their outer layers to get down to or below this 1.4 solar mass limit in the core and form a white dwarf. And that's a stable configuration that will never do anything else. If nothing else happens to it, it will just cool off and sit there forever and become a cold, dark cinder in space.
Right. It's important to point out they're not burning. They're not shining in any way other than the energy from the compression, I guess, right?
No, they're shining. That we see, they're shining because they're still hot from the nuclear burning phase, but they're just cooling down. So they're cooling curves, and all of this is pretty well understood. So they're just shining by releasing the heat, the thermal energy that heated them up in the first place, and
right.
They don't have any way to produce any more energy, so that's why they'll just become cold, dead cinders. Now, electron degeneracy is a very interesting physical phenomenon that was discovered by Chandrasekhar we have a very nearby star, Sirius, the brightest star in the sky, and it has a white dwarf companion, and it's far enough away and the star is close enough we can actually resolve them visually, and he was concerned about what this very hot dim star was. It was a companion to Sirius as a normal A star, a big bright thing, but here's this little hot thing which is much hotter than Sirius, and at the time Chandrasekhar worked, there was no explanation for such an object. It seemed impossible, and he derived this solution that the thing has become, the core has condensed and become so dense. A white dwarf, as Boris said, is a mass of 60%, 80% up to the Chandrasekhar limit of the Sun, but in a volume equal to the size of the Earth. So the density inside is huge, and at these densities, what Chandrasekhar realized is that electrons no longer belong to individual nuclei. There's just a sea of electrons in this object, and the nuclei are all separate. The electrons are kind of all shared, and that's what electron degeneracy means. And this is a stable quasi, or like solid or quasi-crystalline state that will hold up the remnants of this star, this core, forever against the force of gravity.
Yeah, I've always oversimplified it by imagining this star with all of the electrons are squished so tightly together that they're not, like you say, they're not part of an individual atom anymore. There's just no more space there, and they're all kind of tightly packed into this sort of, well, as you said, maybe a crystalline kind of structure. Not really, but.
And just kind of wrap that up. So there we have this white dwarf then, so it'll just sit there forever. But if you have some mechanism of dumping more material onto it, or merging two of them such that you exceed that 1.4 solar mass limit, then you're going to get a 1A supernova.
And there you go. So good job. That was a tough concept. So I hope that made a lot of sense. I find that these my favorite thing about it is you can always use the word degenerate now in astronomy and have it mean something good. And that's also true with double degeneracy. So, okay, so there was a question here I wanted to get to. A comment from Russell Bateman. This one's to you, Carol. This is off topic, he says, but is that 3D printing going on in the background?
Yes, it's 3D printing going on in the background. We have a project to create objects with a 3D printer, actually for the visually impaired. And unfortunately, because the printer's in my office, the intern sets up the job and it runs for 7 hours, and there's nothing I can do.
Well, I'll help you with that. Send it on over my way, and I'll take care of it for you.
It's trying to make a galaxy, only a really big one, in fluorescent orange, and we put textures on them so they can feel what it feels like since they can't see the images. We haven't figured out how to make a white dwarf or a cataclysmic variable yet. Maybe just one of the spheres would do as a surrogate for a white dwarf.
Yeah. So there you go. Yeah, it's really a cool printer too.
So many apologies for the noise.
No, it's great. It's we probably should have a hangout on that at some point. 3D printing and uses in astronomy. So, Emmanuel Conceal, I believe is how you pronounce his last name, was pointing out that observation campaigns, past and current, for pro-am collaboration are available on the ABSO website. And he says it's at abso.org/observing-campaigns. So you can get a sense of what's going on already. Right, Arnie? So you can kind of already get an overview of what's being done within ABSO, AVSO. Okay, so
well, that brings up a point. I had a question about the observation that they were taking, that Arto and Gordon were doing for Boris. Was there a lot of communication among you? Like, oh, I observed it and it's blah blah, magnitude, or do you just basically send things to Boris and to the AVSO for further processing? So how much communication in these campaigns goes on between the AVSO members?
Yeah.
Maybe Gordon and Arto could explain that.
Yeah, primarily it was by submitting the data to the AAVSO website, so it was kind of an indirect communication like with Arto and others. Now, when things got really kind of critical, the last 24 hours, then there were occasional emails going back and forth between us directly, because everybody was trying to get the observation that the HST needed.
Yeah, that's true. how it happened.
And do you both join campaigns regularly?
Yeah, I mean, in my case, yeah, I do. I mean, to me, that's the enjoyment of the amateur astronomy. I think people go one of two ways in amateur astronomy: the beautiful photographs or science support. In my particular events, working with the scientists.
Yeah,
And how about you, Arto? You do the same? Is that the same?
Same for me. Yeah, same for me.
Great, thank you.
All right, so Christian Alexander Wiederer is asking where, and this maybe Nolan, you know, or Carol, where can I find an overview about all HST observation orders, or any statistics about the observations, and also about the usage of color filters, things like that? Is there a place people can go to see where HST is about to observe?
Yes, actually, I just looked it up, and you can go to the website, which I will tell you, but you can also do a Google search on HST observing programs, and there is a page that talks about the programs that are in the queue for the week. Nolan talked about that there's a queue built for a week, so you can actually look at the observations for a week, and then we have this process where every year we have proposals like Boris and others put in a proposal to get time on HST, and then they're peer reviewed, and the calendar, then those proposals that won are published as well. And all of those are through the Hubble Space Telescope Mission Office webpage, which is from the Space Telescope page. So I will say it slowly, and it's www, of course, .stsci, which stands for Space Telescope Science Institute.edu. And if you go to that page and you look under missions, there's HST mission, and all the things about the observations in what's called Cycle 21. Cycle 22 was just peer-reviewed, and that will be published soon. All the previous cycles of things that have been observed. We, of course, have our press releases that highlight some of the discoveries, and then there is the schedule that says HST program for the week. So you can see what's happening for the week. So all that information is out there for you to peruse.
Young astronomer there.
Yeah,
a budding astronomer.
Okay, so I want to respond to one comment I'm seeing on here about there aren't any answered questions showing up under the Q&A app, and the reason for that is I don't have the ability to select them. I am not running the Hangout, so I don't get the ability to actually choose which questions. But we are answering questions right now. I just can't select them and have them be highlighted. And I'm going to work with Elena on fixing that next week. So I just wanted to let people know that is we are answering questions. So so that was good. So let's see. Well, finally, we'll take. Let me, Scott. Am I missing any? Have you been looking by any chance at the comment tracker? I've been looking primarily at the
I've been
Q&A
looking,
app.
and a lot of our stuff is on the Q&A app. Although I am blowing up the Hubble Hangout Twitter feed, so go Twitter.
Awesome, great. So let me check that real quick. And oh, you are. Look at all that. Great job. So
the Q&A app has been fantic.
Yeah,
I love that you guys are using it.
Yeah, so that's been the primary way people have been interacting with us. So thank you guys for that. So where are we going for here? What's next? Oh, Boris left. Okay.
No, I'm still here.
He's still there.
Oh, you are there. Oh, thank goodness. I thought you dropped out. Oh,
yeah,
okay.
I dropped out, but I joined again.
Oh, good, good. So what's next? Where are you just going to keep analyzing data, or do you have any? What? Tell us what to look for.
Well, so we'll be busy with that data set for a while. I've got some other HST programs, but nothing on exploding white dwarfs. So that's a completely different story there.
Okay.
So Boris is one of our most successful Hubble proposers, and every cycle he's on multiple proposals. I don't know how many for this cycle, but I know it's more than 2 or 3.
Well, that's a good point. I mean, he got 122 orbits for this particular. That's a lot of time. That's a lot.
We've gotten other ones as well. So, how many are you on this cycle, Boris?
I think 6. So one is a PI and 5 as co-eyes.
Wow. Nice.
Good. We'll have you back.
Nice.
I can see that
Keeps us
already.
busy.
Yeah.
Yeah, so Eric Charland has commented that, great idea, Tony. I'd watch for sure. Living in a big city, no point in buying a big telescope. You know, this virtual telescope idea really is...
It's fantastic.
Yeah, I love the possibilities for it. You can use a telescope on the other side of the world, get your data, and contribute to science. I mean, that's...
I love seeing it being used this way because we use them every once in a while for the virtual star party. So we have friends at iTelescope that do let us use them for the show.
Oh, that's nice.
And so we get to see amazing views from across the world that's not necessarily from our astronomers that are in. So seeing it being used for science in this way and really supporting the Hubble Space Telescope, I mean, it's something that I think is fantastic. People think that being able to do science with a space observatory is so far away from them, but it's something that you can really take part in, and there's it's not a big threshold to get into. There's a lot of resources available to let you actively contribute to science that's being done today.
Well, it sounds like
3D
it's not.
printer explodes.
Yeah, it sounds like it's not a zero. Yeah, Carol, it sounds like it's a non-zero cost though. There's still money involved and things like that.
Definitely it can get expensive depending on how much time you observe. On the other hand, if you're just tracking, a couple of stars and measuring their magnitudes, once a day, it's not that bad.
We didn't talk much about the processing. I mean, so Scott, you said people have used them on virtual star. Don't you have to process these images? They come back needing dark subtractions and all kinds of things, right? I mean, you can't just throw them up there. Is that true?
Some of them that we've used with iTelescope have just used regular color cameras, so we haven't used any of the scientific data coming through it. We're just using the photographs that are coming down from the cameras that we've used, which we have like a 1/2 meter telescope, which is great to use for beautiful photography. I don't know about you guys with your scientific observations. What data are you receiving from the detector, and how do you process that before you're sending it off to the Hubble team?
Yeah, we actually get, you download all the images from the scopes directly onto your laptop computer, right? And then you process all those and get the magnitude measurements, and it uploads those back to the AABSO website. So, that's how we get the data from the remote site.
I want an app. I want to be able to go out and I want an app. I'm going to point it up in the sky and have Hubble use my stuff.
I'm sure Arnie's working on it.
Okay, I got one final question. It's very it's one of the older ones, and it's got 2 pluses, so I want to make sure I mention it. It's from Ganu Raju. I'm in India. India is in Asia. Asia is on Earth. Earth is in the universe. Universe is in a galaxy. Well, other way around. But where is the galaxy, and how long is it? So I guess the simple answer might be that the galaxy is one of a much larger structure of other galaxies around us. We're in something called the local group, and those galaxies are kind of merging. In fact, we're on the way of colliding with one of them right now, the Andromeda Galaxy. But on the much larger scale, the universe is composed of this structure of galaxies, all of which are interacting in a variety of complicated ways, but overall the universe is also expanding and accelerating. So it's good to point out that you start in one spot, and as your scale gets larger, the kinds of things that become important change a little bit with the scale that you're looking at. So thank you for that question. And I guess, guys, I want to thank everybody, Boris, Nolan, Arto, and Gordon, and everybody. Thank you very much for joining us. This was a really great hangout. Carol, Scott, awesome as always. A lot of fun. I want to thank you guys for watching. I will still monitor all of those channels for a while to answer your questions if you still have some. I want to thank you all for watching. Next week, we have a Hubble Hangout. What's up next week, Carol?
Oh, you would I don't know. Keep talking.
Yeah, I did that to you on purpose because I didn't have the schedule in front of me either.
Maybe Scott can answer.
I can Google that as well. Let me get in my calendar and find out.
No, I haven't put the event up, which is why. Yeah, no, I put it on the spot. That was unfair. July 17th, we're going to be talking about planetary aurora. Lemmy. And we're going to be looking at far UV observations using HST, and so we hope you'll join us for that. That's the same bat time, same Hubble time, same Hubble channel.
There you go.
So that's looking at, see, not only Earth have aurora, but the other planets in the solar system, and he's going to talk about that.
Right. So we hope you'll join us, and we have and bring us your questions and comments. That's it for this time, folks. Thank you all for watching, and as always, keep looking up. Hey app. You'll see that if you're watching this on YouTube or on the Google Plus event page. Just type in a question or a comment, and we'll see it come up on our window pane. Also, the YouTube comments. Feel free to leave a comment there. You can tweet using the Hubble Hangout hashtag. One day I'll get that without stumbling.
You got it.
I'm monitoring that on as well as the Google Plus event page. So there's lots of ways for you to leave us comments. Scott, Carol, and I are looking at all of those, so we encourage you to ask us questions. Okay, so today we have with us from the University of Warwick, we have Dr. Boris Gensecki. He was the PI of the program, and he will be giving us a background of some of the scientific motivations and what they were doing, what they were trying to accomplish scientifically with the Hubble Space Telescope. Also, Dr. Nolan Walburn, also of the Space Telescope Science Institute. He's a member of the COS team and the Cosmic Origin Spectrograph team, who was also responsible for various things on the project. Alan Welty is here. No, he's not here. I'm sorry, Alan. He did. And we have Gordon Meyer and Ardo Oksanen from who were two. And here's what
to Type 1a supernovae. And so the system that we were interested in are called cataclysmic variables. And in those systems, you have a white dwarf that is accreting material from a relatively low mass companion star, so something like the Sun or even less massive than the Sun. And
I think Scott might have a diagram on that real quick to put up.
Okay.
Here we go. Go ahead. So yeah, this is just showing what Boris is talking about.
Okay, so in a cataclysmic variable, you have a white dwarf that accretes material from that companion star, and you form an accretion disk of mainly hydrogen that then flows onto the white dwarf. And probably 20, 30 years ago, astronomers have excluded these kind of systems as potential Type 1a progenitors because they go periodically through a process which is called the classical nova, where the hydrogen that flows on the surface of the white dwarf starts to burn and then ejects all the material that has been accreted back into space. And so if that really is true, these white dwarfs, they couldn't grow in mass. Yet there are some question marks to those problems, and some recent studies suggest that, well, the white dwarfs in cataclysmic variables. And we're live.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we've got a really interesting hangout planned for you today. We're going to be talking about white dwarfs, cataclysmic variables, the Hubble Space Telescope, amateur astronomers, all kinds of really interesting topics today. So the basic premise of today is the astronomers using the Hubble Space Telescope wanted to try and answer the question, can white dwarf stars grow in mass, among other things. That's one of the questions they were trying to answer. And today we're going to explore that. With me today, as always, is my good friend and colleague, Dr. Carol Christian. She's from the Space Telescope Science Institute also. She knows about all things Hubble, and she's going to be helping me with this discussion. Also is Scott Lewis from knowthecosmos.com. And he'll be on hand to help provide his unique perspective as well. Before I get to the introductions of our group today, though, I want to point out that we hope you'll interact with us. We hope you'll send questions. Already, I'm encouraged by what I see in the Q&A app. There's already a lot of things there for us to get to, and we're going to, I promise, we'll get to as many as we can throughout the course of the discussion. But if you're wondering how you can interact, one of them is the Q&A. Boris describes them. He describes them as two of the most professional amateurs you can imagine. They operated remote telescopes, and without them, we would certainly have struggled to complete this HST program. So welcome, guys. We also have Arnie Hendon from the American Association for Variable Star Observers. He was responsible for organizing some of the campaigns. So welcome, Arnie. And we also, and I think that covers everybody. So let's go ahead and get started. And Boris, I'd like to start with you as the PI. Give us some background of what you were trying to accomplish with this. You had been given 122 Hubble orbits to accomplish what you wanted to accomplish. So give us a background. What were you trying to do?
Okay, Tony. So I guess you've talked about Type 1a supernova in past hangouts, which are among the most powerful explosions in the universe, and they have been used to discover dark energy, and led to the Nobel Prize in Physics in 2011. And one big problem is that we still don't know exactly what kind of stars explode under what conditions to make a Type 1a supernova. Now, most astronomers agree that it's probably white dwarfs that reach the so-called Chandrasekhar limit, a maximum limit that they have, and then they explode. And that means these white dwarfs need in some way to grow in mass. And so that was the key question we want to address in one type of white dwarfs in binary stars.
Okay, Boris, let me just interrupt you very briefly for a moment here and say one important thing about Type 1a supernovae that I want to make sure we mention, and that is they are basically cosmic yardsticks. They are very important for measuring how far away things are in the universe, because when they do explode, they explode with a known intrinsic brightness, and that is a brightness that they would be if they were right next to us. And if we see how bright they are very far away, and we know how the light falls off with distance, we can figure out how far they are. So that's why Type 1a supernovae are so important. And as Boris said, we don't know exactly the kinds of stars that cause them, which I guess surprises me, Boris. I thought we did have a good handle on that.
Well, it depends on the fashion that you follow a bit. At the moment, probably most people would say that they believe it's merging double white dwarfs, two white dwarfs that merge together and then exceed the Chandrasekhar limit, but there's still quite a number of problems with that model as well. So we wanted to explore an alternative route that may